Well, a very warm welcome to this lunchtime's webinar, Is Earth Unique in the Universe? My name is Cathie Clarke. I'm a professor at the Institute of Astronomy and currently one of the co-directors of that institute. My own research concerns the formation of planets and the environments in which they form, the disks out of which they coalesce. And so I'm one of the very many researchers at the moment in Cambridge who are working on topics which are kind of adjacent to the theme of today's seminar, which is to do with life in the universe. This is a big theme across Cambridge, as you'll be hearing later. We have a dedicated Leverhulme Centre for Life in the Universe, which combines researchers from many different disciplines looking at this extremely important question from different angles. And we also have a dedicated master's programme on planetary science and life in the universe to train up the new generation of people with the right multidisciplinary skills to address this topic. But today we have speakers who are working right at the very heart of this debate, coming at it from two quite different angles, from the astronomical and from the geochemical directions. Those of you who haven't read a recent email will be disappointed to learn that unfortunately our third speaker today, Dr. Amy Bonsor, is not able to join today due to illness. So while we regret this, we still have plenty in store for you from our other two speakers. Now, this is one of a series of webinars which spotlight research across the School of Physical Sciences in Cambridge. And we've been working on this in conjunction with our colleagues in the Development and Alumni Relations Office. The format today is quite simple. Each of our speakers will speak for about 15 minutes. You'll have opportunities to put questions in using the Q&A button at the bottom of your screen. And then we will have around 20 minutes of questions at the end and wrap up. So I'm looking forward to a fascinating hour ahead, looking at a variety of topics on this most compelling of themes. So without further ado, I'd like to turn to our first speaker. This is Professor Nikku Madhusudhan, who's at the Institute of Astronomy, and he will be telling you about the astronomical perspective on the prospects of life in the universe. I do thank you.
Can you see my slides okay? Great. Hello, everyone. It's a great pleasure and a privilege to be speaking to you today and sharing some of the excitement at the very cutting edge of exoplanet science, specifically towards the search for life elsewhere in the universe. So I'm Nikku Madhusudhan. I am at the Institute of Astronomy, University of Cambridge. We have a big team here which works with state-of-the-art observations, astronomical observations, especially focused on atmospheres of exoplanets and to see if we can detect signatures of life on planets that are potentially habitable. So I'm going to take you to the very cutting edge of this topic today called the Hessian paradigm. We are trying to come up with new kinds of planets that could be potentially habitable, stretching our imagination on where else, what are the various environments where life could be prevalent in the universe, and see if we can actually detect signatures of such life. So to start with, if we really zoom out as a big picture, if we want to understand what is the frequency of life elsewhere in the universe, currently we have the n equals to 1 problem, which is that we know of literally only one planet where we know that's true. That's the Earth. So when we look at planets elsewhere in search for life, it is obvious for us and it's natural for us to focus on Earth-like planets like this. However, there are observational challenges, there are technical challenges in observing Earth-like planets because these are small planets, and especially if you have them around sun-like stars, that contrast between the star and the planet and the star, be it in size or in brightness, is such that that's below the limit of what current facilities can do. So So when we look at exoplanets, we try to be a little bit broader in the kinds of environments we're looking at, maybe slightly bigger planets, maybe slightly smaller stars, to make them observationally favorable. And that is basically what is driving the search for life right now, that sort of approach in this field. So exoplanet demographics, you may have already heard about this, that exoplanets, by exoplanets, I mean planets around other stars. These are extremely common and extremely diverse. We know of close to 6,000 planets around other stars right now, just in the last, discovered just in the last 30 years. And if you look at the demographics of these planets, like what sizes they are, what are their orbital parameters, and so on, what we find is that they basically span the entire range of planetary parameters that we can think of, like their masses, radii, orbital parameters. All of these are extremely diverse. And more importantly, these small planets that are between Earth and Neptune in size dominate the exoplanet population. And that's very relevant for the current topic, to search for habitable conditions and signatures of life elsewhere. So there are several facilities that have been operating until recently. Kepler space mission was very successful. TESS is another NASA space mission that has been very successful, and there are CHEOPS is happening right now, and there is a new mission from ESA, the European Space Agency, that's coming very soon, the Plato mission. So we are detecting lots of these planets and all kinds of planets out there. Now, if we take again a step back and ask, what are the fundamental questions we're trying to solve in exoplanet science as a whole? Then there are three broad questions that encompass basically everything that we do in this field. How do planets form and evolve? This is the topic that Cathie alluded to earlier. Just understanding the formation, the origins, and migration pathways of these planets at the very early stages. So we want to understand that, and that will tell us how unique is our own solar system from a pure formation and architectural point of view. We also want to understand how diverse the planetary processes on these planets. And then ultimately, the big question is, are we alone? Right? So this is the remit of exoplanet science. And in today's talk, we are going to focus on the third question: are we alone? Now we go back to this plot. I showed you a variant of this demographics plot in a previous slide. But what I want you to really focus now is this: the y-axis is showing the radius, the size of the planet. And you'll see that the sizes of Earth, Neptune, and Jupiter are marked here. And you see a high density of points between Earth and Neptune in size. This is what I mentioned earlier, is that these planets dominate the exoplanet population. But those planets don't have any analog in the solar system. We don't know of any planet that is between Earth and Neptune in size. And there are several missions that are detecting such planets, and new spectroscopic facilities like the HST and the James Webb Space Telescope, which just started a few years ago, which are trying to understand their atmospheric composition. So this talk, I'm going to focus entirely on planets in this regime, because those are the planets that are the environments where we are looking for life. To hone in a little bit further on this specific topic, the planets, if you look at terrestrial planets, they're dominated by carbon dioxide, nitrogen, oxygen-rich atmospheres, whereas Neptune is a hydrogen-rich atmosphere. And as I mentioned, there is no planet in the solar system that's in between. So it's entirely up to anyone's imagination what these planets are like. Are these planets in the sub-Neptune regime larger versions of the rocky planets, or are they smaller versions of Neptunes? We have no idea. So just from the mass and radius measurements, the bulk properties, there is no way of knowing what their atmospheres are like. So we need to make spectroscopic observations. At the same time, we also need new theoretical developments to understand how far can we stretch the boundaries of our definitions of habitability of planets. Which of these planets can be potentially habitable? How big can a planet be? What kind of an atmosphere can it have and still be habitable? So these are some of the big theoretical questions we're asking, and also which are driving the observations in the field as we speak. Now, if you talk about what kinds of planets are habitable, if you look at Earth-like planets, the nominal definition is one of the classical habitable zone, which is the distance from the star, where if you place an Earth-like planet, it can sustain liquid water on the surface. So this is a band here that you're seeing, this blue region, for different star types. So if you go to smaller stars, they're also cooler, so you can be closer to the star and still be habitable. Whereas for sun-like or larger stars, the habitable zone is farther out. So this is just a cartoon from very early on. These definitions changed over time, but the principle remains the same, that you need to be at the right distance. Now we want to ask, theoretically, what are the limits on the planet mass, radius, temperature for habitability? And there is a lot of work going on in this direction, and I'll just introduce the Haitian habitable zone here, where in recent years we have come up with this new concept of planets which are larger, which can be larger than Earth, more massive than Earth, but because they have hydrogen-rich atmospheres, they can sustain habitable conditions for much longer. Because hydrogen is a very good greenhouse gas, you can be much farther from the planet and still retain the necessary heat. Haitian stands for hydrogen and ocean. It's a portmanteau of those two words, hydrogen and ocean. These are planets where the surface would be covered entirely in oceans and the atmospheres would be made of molecular hydrogen. And that combination gives you certain properties which allow these planets to remain habitable for much farther, wider orbital separations from their host stars. So to give you a sense of what these planets would look like, if you stand on one, this is what it would look like. It will be a warm ocean-covered surface. Around most of these planets, candidates we have identified are around red dwarf stars, so small M dwarf stars, and their atmospheres would be hazy and hydrogen-rich. So all well and good for the theoretical side of things. What we have identified is that your planets can in principle be larger than Earth, slightly hotter than Earth, farther or slightly closer than the Earth's habitable zone around an M dwarf. But is it observable? So in recent years, again, we made a prediction that K218b, a sub-Neptune planet, could be a good candidate for such a Haitian world. The planet is just over 9 Earth masses, about 2.5 Earth radii, but the insolation it receives from the star, the irradiation, is very much like Earth. Okay, so it is, if it were an Earth-like planet, it would be habitable at that distance, but it's slightly larger. So this is where we wanted to do atmospheric observations of this planet. Now I want to introduce you to transit spectroscopy, how we characterize atmospheres of exoplanets. So this is the case where a planet goes in front of the star and you're seeing some of the starlight passing through the atmosphere of the planet and getting absorbed by some of the molecules in the planet's atmosphere. So what you plot here at the bottom is absorption of starlight due to the planet's atmosphere as a function of wavelength. Okay, this is an example spectrum obtained with the Hubble Space Telescope more than a decade ago. Okay, I just want to show you what the big breakthroughs that the James Webb Space Telescope is allowing. It's the largest telescope that has ever been built in space. And I'll show you the big difference. So with the Hubble Space Telescope, we had spectra like this. With the James Webb Space Telescope, you have spectra like these. Okay, so the difference is that there's a much wider wavelength range. If I toggle back and forth, you see that this entirety is below 2 micron infrared in the infrared. But if you go to JWST, you are sensitive to now much wider wavelength range. This can keep going actually up to 10 micron or even above. And then the sensitivity, the error bars are much smaller than what you would have obtained for JWST. So this is doing phenomenal advances in all kinds of atmospheric characterization of diverse planets. This is, I'm showing you just a giant planet here, for example. Now let's look at what it would mean for a candidate Haitian world, the sub-Neptune we are talking about. To give you a sense of scale, this was a spectrum obtained with the Hubble Space Telescope with over 50 hours of Hubble time, okay, of HST time, telescope time. Now, with James Webb Space Telescope, we were offered time to look at this same planet, and in just 14 hours, just watch this spectral range, just between 1 and 2 micron, right? In just 14 hours, we got a spectrum like this, okay? Between 1 to 5 micron, and you can see multiple features of various molecules. So this solves lots of open questions in the field. One of the big discoveries this enabled is the robust detection of methane in the atmosphere of a small planet, regardless of whether it's habitable or not. That itself was a huge breakthrough in the field, which has never been possible before. And similarly, there were other species for which we got good constraints. We were seeing some evidence for carbon dioxide and a very tentative evidence, and we are not sure about that yet, but a tentative evidence for dimethyl sulfide, which is a potential biomarker that has been predicted for planets like this. Okay, so we are able to detect atmospheric signatures already of these potentially habitable planets. Then you may ask, the question, well, what are all the kinds of molecules you can detect? I'm just showing you here various molecules which have contributions. These are all just model spectra. Here, the points with error bars are the data. And you can see that various molecules have strong spectral features in this wavelength range. So in principle, we should be able to detect these molecules if they're present in significant quantities. Now, you may also ask, well, did you just get lucky with one planet like K218b? The answer is no. Just in the past year, we looked at data from yet another exoplanet. This is TOI-270d, and you can see the remarkable similarity between the methane features, for example. And we also detected a new molecule called carbon disulfide, which is also a potential biomarker, but it could also be produced by other means, so we are not sure yet. But the excitement surrounding all these developments, observational developments, is A, this is the first time in human history this has ever been possible to even look at such planets. Okay. And B, there is a real chance that some of these planets could be habitable and we might be able to detect biosignatures in the foreseeable future. So this is where the big breakthroughs are happening. Now, what is like a potential biosignature? If you look at Earth-like planets, you would say, oh, I want to detect oxygen or ozone or methane, nitrous oxide, and so on. Turns out those same species may or may not be a good biosignature on a Haitian world with a hydrogen-rich atmosphere. So what we do is we look at a lot of other molecules like dimethyl sulfide, which I just talked about, and there are several other species like that, organosulfur compounds, which can act as good biomarkers in Haitian worlds. And now we have the sensitivity with JWST to actually look at them. And you can also ask, well, we have detected this species, but how do we know what the actual surface conditions and interior conditions will be like? And there we turn to theoretical models, where this is just one example. It's a slightly complicated plot, but I'll summarize it by saying that based on the atmospheric properties that we derive from the spectroscopic observations, we can extrapolate them into the internal structure to put constraints on the internal structure models. And you can see here different kinds of internal structures that are possible with these observations, all with different thicknesses of hydrogen, helium, or like the ocean layer below the hydrogen atmosphere. And this is the key plot here. If you ask how deep is the ocean on Earth, it's order 10 kilometers, right? But if you look at the Haitian world with an ocean-covered surface and ask how deep can the ocean be, it could literally be hundreds of kilometers. And that opens a wide range of other questions. And well, if you have that deep ocean, what would life be like? What would the ocean conditions be like? Well, do you have an ocean floor? Probably not. It's just ice, high pressure ice at the bottom. So these are all like rich theoretical questions that have just opened up based on the observations we are making. So these are major breakthroughs that are happening on the observational side and on the theoretical sides. And while that's happening, there is already several hundreds of hours of JWST time allocated for looking at several Haitian worlds, order 10 to a dozen of Haitian worlds, some more observable than others. But in the next couple of years, these are the kinds of observations we will be making. And hopefully, if these things are actually habitable and have life on them, we might detect some potential biosignatures. So I would like to end by saying this decade is basically serving already as the launch pad in the search for life on extraterrestrial worlds, on exoplanets. There are big telescopes, the James Webb Space Telescope, obviously, as you just showed, but there are also extremely large ground-based telescope coming, a 40-meter diameter telescope from ESO, from the European consortium. And these are the kinds of telescopes that will allow us to explore these strange, exotic worlds that we have no analogs in the solar system. And hopefully, we might find a signature of a potential biomarker. So in my mind, the question is not if we would find a candidate biosignature. We might actually find, we do have the sensitivity in the next several years or maybe within this decade. But a bigger question in my mind is whether we are actually prepared to identify life if we do find a signature. In other words, are we prepared to find life as we don't know it? Thank you.
Thank you very much, Madhu, for that fascinating tour of theoretical work combined with what we can learn from cutting-edge instruments such as the JWST. I'd like to remind everybody to put your questions into the Q&A, and we'll be dealing with them after Nick has given his talk. But thanks again for that, Madhu. Now we're turning to something very different. Professor Nicholas Tosca from the Department of Earth Sciences will be approaching the whole question of life in the universe from a different perspective.
Thanks very much, Cathie. My name is Nick Tosca, and I'm an earth scientist, although I'm also a geochemist. So that's someone who applies chemistry to understand and interpret the processes that, in my case, shape the composition of natural waters. Our research group integrates theory, experiments, and fieldwork to address a whole range of problems, including the coevolution of seawater chemistry and climate through Earth's history, the environmental conditions that might have promoted the synthesis of molecular building blocks, which I'll talk about in a moment, at the origin of life on Earth, the chemical evolution of a wide range of natural waters on Earth, and also unraveling the chemical evolution of ancient environments on the surface of Mars. What I want to talk about today in just a couple of minutes is another question that's intimately tied to what Madhu talked about, the question of whether life exists elsewhere beyond the Earth. And the question that I'm going to focus on is how life originated on Earth. Now, here at Cambridge, there's a whole community of folks who are working to address this question, and it's arguably one of the greatest interdisciplinary challenges of our time. I myself can think of few questions more fundamental and ancient than the question of how life arose and whether we're unique in the universe. The answer is, I think, intimately tied to every human's concept of what it means to be alive. One thing that's important to emphasize, though, in serious scientific study of the origins of life on Earth is that we can't hope to achieve a unique solution to the problems of the origin of life on Earth. And in my mind, I think that's aptly summarized by a fantastic quote by the great Swiss chemist Albert Eschenmoser. And he said that the origin of life cannot be discovered, it must be reinvented. And that is indeed the track that chemists and earth scientists and molecular biologists are taking. And over the last 10 to 15 years or so, there have been major breakthroughs in all of these subdisciplines, which now means that we are arguably on the verge of knowing whether a relatively simple pathway to life is possible, and whether or not that pathway is highly complex and therefore improbable. So the answers to these two important questions, are we alone, and how did life originate, I think hangs on a third question, which is, how likely is it for life to emerge on the surface of a potentially habitable planet? And that there are at least two ways to address this particular problem. So first is, of course, through laboratory studies of the transition from chemistry to biology. The second approach would be the search for life on other planets, which is what Madhu spoke about in his talk. But as a geochemist, I'm lucky enough to be involved in both approaches in a way. So in my day job, I run a chemistry laboratory here focused on understanding how the pathways to synthesize life's molecular building blocks might have functioned in the natural environment. And what this tells us about the processes and places within which this could have happened. We work with organic chemists who are trying to synthesize these molecules, and really we're interested in attaching with some specifics what environments and what processes really needed to take place in order for these pathways to be viable. By night, or at least that was the case in the early days of the mission, when I was up late at all hours of the night while the rover was roving on Mars. So I'm a scientist on the Mars 2020 Perseverance rover. And actually what you're watching now is video footage of the real-time landing of the rover back in 2021. And my job on that mission is to unravel the chemistry that transpired in ancient environments on the surface of Mars and what that might have meant for the prospects of life on that planet. And even more than that, I think it's arguably a much bigger responsibility, is that we also have to choose the samples to send back to Earth on a future mission, because one of the only ways to really know whether life existed on ancient Mars is, of course, to analyze and probe the samples in laboratories here on Earth. Now, the fascinating thing I think about this particular question, how could life have originated on a potentially habitable planet, is that success in one aspect of this could strongly impact the other. So, an example is that if we found a path from chemistry to life in a laboratory, say, we might conclude that nature could do it too, especially given the hugely diverse range of environments available at nature's disposal and eons of geological time. And in fact, if we could be specific about the sequence of events and processes and environmental conditions required for a particular pathway to life, we could then assess the likelihood of that pathway ever existing or taking place on other planets, at least in reference to that particular scenario. But on the flip side, if we were ever to discover evidence of extraterrestrial life, say microbial life, biochemically simple life, at least as we're familiar with on this planet, then we might conclude that a reasonable geochemical pathway to life does exist, and the recipe, as it were, isn't as difficult as we thought. So, working on this problem at a place like Cambridge has been hugely exciting. I think in part because we've assembled a huge sort of community of scholars that are really committed to working on these problems from these different complementary perspectives. Certainly at Cambridge, we see the synergy in addressing both of these at once. As an example, the photo that you're looking at now is from the launch of the Leverhulme Center for the Life in the Universe, which is a 10 million pound, 10-year initiative. It was launched in 2021, and really the idea is that in Cambridge, if we're going to work on something this big and this important, at the same time this risky, we want the flexibility and the freedom to be able to harness all these breakthroughs across these different subdisciplines to collaborate in a way that's, in my mind, simply not possible under sort of standard research council funding structures. So along with this, as Cathie mentioned earlier, there's been a recent launch of the Planetary Science and Life in the Universe Master's Program, led by Ollie Shortle. And this is a unique interdisciplinary course. The idea here is that we'll be cultivating a new generation of scholars who will shape this highly interdisciplinary research thread and kind of guide it into the long-term future. So, at this point, some attendees might be asking, what does Mars have to do with all of this? So I kind of mentioned Mars as an important part of the question of knowing whether life could have originated on a potentially habitable planet. But Mars is arguably the most important case study in what we refer to as planetary habitability. In many respects, Mars is about as close as we can come to the Earth. In a planetary dimension, it's composed essentially of the same chemical building blocks as the Earth. It has an atmosphere composed of similar gases that exist in Earth's atmosphere, although at different proportions. And decades ago, we discovered that Mars hosted liquid water at its surface billions of years ago. And this implies that the ancient climate on Mars must have stabilized liquid water. But Mars is also, I think, special for another reason, in that Mars contains a record of ancient environments that exists nowhere else in the solar system. And that includes the Earth, too. In studying the origin of life on Earth, I think a crucial question, that many of us ask is what do we know about the earliest environments on Earth, and what were those environments like at the time that life originated? And the difficult part of answering this question is we don't have any leftover materials from that time period on Earth to study. And this is mainly because Earth is a planet that experiences plate tectonics. This is the process of recycling and destroying our own continental and oceanic crust. And that means that much of the record of the earliest part of our own history has been erased forever. Now, Mars never had plate tectonics, and so much of what happened during its early history is actually recorded in exquisite detail within sedimentary rocks preserved at its surface. And these sedimentary rocks are a lot like books in a way. You can read them almost page by page and try to unravel the processes, the environments, the chemistry that took place at this particular time and place on the planet. And importantly, what the water chemistry was like early in Mars's history. And that's something that we just don't have access to on our own planet. So by studying ancient environments on Mars, we've discovered a bunch of different things. We've discovered chemical reactions that occurred in water under primitive reducing atmospheres that generated things like hydrogen that might have served as an energy source for primitive chemical reactions. We've discovered a lot about the ancient sulfur cycle and how climates function under very high partial pressures of CO2, which both are quite relevant to the earliest history on our own planet and may have fed into environmental conditions that could have favored the origins of life. The flip side, though, is that Mars wasn't always a nice place to be. So although it had liquid water at some times during its earliest history, it turns out that wild climate fluctuations, there, at least from which we've been able to infer from the record of early environments preserved at its surface, mean that water was only intermittently present, with intervals punctuated by cold, dry conditions. And eventually, in the long term, Mars's water was lost altogether. That this, we think, is mainly a function of the heat released from its smaller core. And at some point, it meant that core stopped convecting, and with the cessation of the convection of Mars's core, it meant that its planetary magnetic field was lost, and therefore it was susceptible to its atmosphere being slowly stripped away by solar wind processes. So, ultimately, we're searching for life on early Mars, and we need to be serious in answering the question of, or trying to answer the question of whether life once existed on Mars, or whether it was habitable but uninhabited, and that's a serious possibility that I think we should consider. But in the end, it's a question that's going to take a lot of time and a lot of hard work to answer. But that the answer is, whatever it is going to be an important one. If Mars wasn't good enough for life to originate, then why? What was it about the earliest history on Mars that was close to, but not exactly like our own history on Earth? Was water not available for long enough? Were climate fluctuations too severe? So my role in the Mars 2020 Perseverance rover mission has provided a really unique opportunity to engage in the science firsthand, and also to take advantage of the chance we have to collect and archive core samples for the future scientific community. This is an enormous responsibility, but it's a really exciting one, because as I alluded to toward the beginning, it won't really be until we get these samples back to laboratories on Earth that we'll be able to say with any confidence that that ancient life, or the signatures of ancient life, are in any way recorded in these particular rocks at this time and place. So I'll leave it there and be happy to take any questions.
Thank you very much, Nick. And the questions have been coming in thick and fast, and now it's my role to select some of them and put them to our speakers. Many of them are going along quite similar lines, so I'm sort of amalgamating some of the questions where I've identified themes coming up. And I think a lot of them are going to be in the general area of, how do we define life? How closely should we be looking for things which are a template of what we find on Earth? So I'll be building those in a few minutes to both speakers. But I'll start with a few which are perhaps more narrowly relating to each of the talks that we've heard. And so I'll select a question which is for Madhu, and something which a number of people have asked is, what are those oceans that you've shown in your artist's impression? What are they made of? Are they H2O, or are they some kind of organic or inorganic liquid?
Yeah, so when we say oceans, we're talking about water oceans, like the oceans on Earth, except they are much deeper. that we expect them to be much deeper than on Earth. We are talking about 100 kilometers or more. So yeah, so they are water-based oceans. And the important bit is also that they are oceans that cover the entire surface. These are ocean worlds with hydrogen-rich atmospheres. So on Earth, we have this combination of oceans and land, and how life evolved on Earth, has a lot to do with that combination. But on ocean worlds, these Haitian worlds, the entirety of the surface is covered with ocean. So there are open questions on how life would originate on such planets as well.
Yeah, can I just pursue that a bit myself as to what extent you've looked into the conditions within those oceans and compared them as sort of crucibles for life compared with our own oceans?
That's a very interesting question, actually, because the moment you pose a planet, you hypothesize a planet that is ocean covered, there are lots of open questions. For example, like in terms of chemical conditions, do the oceans have enough nutrients for life to sustain? Because on Earth, those nutrients come from interaction between the ocean and land, right? So from weathering and so on. Can you have that on an ocean world? So that's an open question. So we had looked at a few years ago, we did the theoretical studies along those lines, and turns out, and that was also surprising to me when we found out the results of those calculations, is that actually, if you take primordial life on Earth several billion years ago, what were their requirements? That is relatively readily satisfied by ocean worlds as well, purely from accretion of impactors from outside or sedimentation from the atmosphere and so on. So that's one example. And then recently we also looked at with a colleague, Emily Mitchell, in zoology. Actually, we tried to say, well, if you have an ocean world, how would the conditions of that ocean impact the possibility of primordial life, like small bacteria at the very beginning of the Earth's history? And we found that with relatively small changes in temperature, you can massively increase or decrease the production of, like, the evolution of microorganisms on such planets. So these are all things that we're looking at. And so far, we haven't encountered a bottleneck, theoretically.
Thank you. And another one is why the focus on the Haitian worlds rather than the more sort of conventional Earth analogues that might also be out there?
Yeah, that's a very good question, actually. So in the field, there are efforts going on in both directions. It's just that when you have Earth analogs, those planets literally, by definition, are Earth size, and you can't have them around sun-like stars because they're much difficult to observe because the planet to star radius ratio, which decides your detectability, is much smaller. So people are looking for Earth-like planets around smaller stars, M-dwarf stars. So in principle, the observability is better than Earth-like planets around sun-like stars, but it's still difficult. So there are hundreds of hours put with JWST on some of these planets. There is a famous system, TRAPPIST-1 system, where there are 4 habitable planets around an M-dwarf small star, and no atmospheric detection has been robustly made so far. So they're just more difficult. So what the approach we are taking here is by saying, well, if we make the planet slightly larger, theoretically, is there a possibility of habitability? And we came up with this solution, is that if you have these ocean worlds and hydrogen-rich atmospheres, they're low density materials, both like hydrogen and water, compared to rocky planets with heavy atmospheres, which means your contrast of the planet to star is better. They become more observable, and we have demonstrated that we can actually observe their atmosphere. So it's purely an observability reason why we are focusing on these planets. And eventually, as time goes and we get better and better observations, we will move to smaller planets. But for now, this is where the frontier is.
Thank you very much. I'll now turn to Nick and ask him some questions. And I think a number of them are based on the kind of technicalities of doing the kind of experiments that he's doing on Mars. For example, it's been asked whether it's better to send the lab to Mars or have sample returns to Earth. And then questions about the concerns about the samples being buried by the Martian sands and how that can be made sure that they are exposed maybe via having a signal generator. Do you want to talk around some of the sort of technical things that people have been pondering here, Nick?
Yeah, that's right. They're all good questions. And maybe it's helpful to kind of clarify a little bit, what we would constitute as evidence for, ancient life and how that would be preserved in these sediments and sedimentary rocks. As I mentioned, with Mars, water is essentially the only game in town, and so because it has, the same chemicals and roughly the same proportions as our own planet, when we think about life, it's a reasonably safe assumption that life may have, been carbon based. I mean, we can't absolutely be sure, but this is all guided on inferences about the history of our own planet. The transition from geochemistry to, biology. And so if that was the case, and in a way, this is the best that we can do, is make that assumption and then go out and say, okay, well, what would we expect to find? The things that we would expect to find that would constitute some of the clearest unambiguous evidence would be, organic compounds, largely carbon-based compounds that would need to have been synthesized by, some biochemical process rather than some, purely chemical process, right? So there are a whole host of complex organic molecules that life and only life makes, for the most part. But a lot of those molecules don't actually survive over geologic time. Keep in mind that these are, sediments and sedimentary rocks that are billions of years old. And so the question is, well, then what molecule do you look for? If the sediments and sedimentary rocks have been sat around for 3 billion years. It actually turns out, and maybe some folks will be comforted to know this, that when we die and we decompose, that the last remnants of our body, the last chemical remnants that will be around for geologic time, will probably be that cheeseburger that we ate last week, because basically the molecules that do the best are derivatives of sterols or cholesterols. They're robust molecules, but they're also synthesized by biochemical processes. And so that has been one component of what we might look for. So fossil molecules, as it were, are often called biomarkers. And these molecules, might be taken as a robust signature of life. Now, in order to detect those, you have to do a lot of complicated, processing, extraction by organic solvents to, remove these organic molecules and then analyze, what are ultimately very, very small concentrations. And that is a really difficult prospect to do with a laboratory, and just sending instruments to Mars. Rather, it's probably easier. And also you have lower gravitational acceleration to deal with and a lower escape velocity to just get the samples out into Mars orbit, connect them with a spacecraft that can then, traverse the Earth and drop them into Earth orbit and analyze them in laboratories on Earth. That's been the approach, but that's not to say that, in situ analysis and human exploration of Mars hasn't been considered, but it's just not in the planning stages as seriously as Mars sample return.
Well, thank you. And I'd like to return in a moment to you, Nick, to talk about plate tectonics. But since you were talking about biomarkers, there was a question which I think would be good also to hear Madhu's take on, which is just about what is actually required in future to be able to identify useful biomarkers in these very different environments.
Yeah, so there are developments in 3 directions basically that are needed. First is just observational. Like this field, the crux of all of this is being able to measure them first, right? So detect them and then see if you can connect them uniquely to life. So first, detectability. So a lot more JWST time and deep observations of some promising targets. And we don't have that many targets. We know of only about a dozen good Haitian candidates, and within that, like about 5 or 6 are already being observed. So good observations, deep observations. Second is the lab-based molecular cross sections for these molecules that we are observing. I mean, you may be surprised to hear that these initial inferences we are making for dimethyl sulfide or molecules like that, these organosulfur molecules, we actually don't have good cross sections for hydrogen-rich environments. Which means like these cross sections, the absorption features that you're seeing, you have to measure those features in a lab, the absorption cross sections, and then put in your theoretical models and then compare the theoretical models to the data to be able to infer them. but we only have that for Earth-like conditions. We don't have them for Haitian conditions. So there's a lot of rejuvenation of experimental work that will happen, in my view, and that should happen to measure these cross sections for a large number of molecules. And the third is the identification part, is that once we detect these molecules, how do you know they are uniquely from like a biological process? And that's where a lot of detailed theoretical modeling is necessary, where you couple atmospheric process with biological process and try to establish that these are actually robust ways to go about identifying them. So yeah, so lab work, observational work, theoretical work, there is work to do in all those directions.
Thank you. Well, looping back to Nick now, this business about plate tectonics and Mars, and there are a number of questions about both the role of plate tectonics in raising up sediments to the surface if you've got subterranean life, and also about more generally the importance of plate tectonics to the evolution of life. Nick, could you talk to those?
Yeah, absolutely. So I think plate tectonics is critical to the long-term evolution of life, at least on our own planet. And a big part of the reason is it regulates how volatile chemicals, so basically water, that the essential solvent with which all of the chemical processes that run life is possible. It regulates the amount of water and its availability through planetary timescales. So the way that plate tectonics works is that there are areas of our crust where subduction happens, where the oceanic crust is subducting below other portions of the crust with different density. That subduction then melts the crust, and the water that's locked up in those subducting slabs then finds its way back up to the surface of the Earth and is outgassed through volcanism again. And that process repeats itself, through time, and it means that the water that's lost through the interior of the Earth, we get back eventually. So it kind of cycles water. Now, if you didn't have any plate tectonics, what happens is the water comes out through volcanic degassing. It gets locked up in the crust, and then there's no way to get that back to the surface environment. There's no way to get it back into the atmosphere if it is locked into the crust in a way that's basically irreversible. And a lot of folks who have been looking deeply into the long-term history of Mars, have concluded that there is evidence that this was in fact the case. So one way that you can monitor how much H2O has been, lost from its planetary budget is to compare isotopes of the heavy version of hydrogen, deuterium, versus the lighter version of hydrogen. And it turns out those ratios suggest that most of Mars's water was lost very early in its history, probably because much of the atmosphere was lost. But in order to explain those data, you need a massive quantity of it locked up in the crust too. And so that I think is the most important part of plate tectonics. It's probably too much of a generalization to say, no plate tectonics equals no life. I think there's much more that we don't know about, how planets could operate and the long-term chemical cycles. But that's one important difference between Mars and Earth that we need to be aware of.
Thanks very much. So I think we're ready to go on to the topic of life as we do not know it, which was, I think, Madhu's final slide. And there have been a number of questions about the ubiquity of carbon-based life. Is silicon-based life considered a possibility? Are we assuming that there are elements that are beyond the periodic table as we know it in other galactic environments? And also questions about what we actually are going to define as life. Is there a kind of ubiquitous definition of that? So I'd like to just hand that over to both of you to comment on this very big question.
Should I go first? Maybe. These are very big questions and very intricate questions, and I don't think we have settled answers on any of those topics. And people can explore various forms of life, and as you said, silicon-based life and so on. But we don't really have a good handle on what the the predictors are for such life. So from an astronomical search perspective, because we are just beginning to even be able to make these observations, we are taking a lot more pragmatic approach. What we are saying is that let's focus on very like primitive kind of life. If you look at, Earth, the early Earth, where you have a lot of ocean and microbial life, what are the gases that the dominant gases in the atmosphere that life could be giving? And let's look for that to establish a zero point, like even as basic as that microbial life, like on Earth, carbon-based, can we actually detect it? So right now in the astronomical sphere, a lot of the practical work is revolving around the practicalities. Can we detect some molecules, some key molecules or not? But how to tie that to the type of life is a question much farther down the road. We are making small steps in that direction. For example, if you literally take the early Earth and change the temperature by 10 degrees or increase or decrease, what perturbations would it cause to the life and hence to the observable signatures? That's the level we are at right now. Um, so that's my answer from the astronomical side of things.
Nick, would you like to chip in?
Yeah, the only other thing to say is that I think there are good reasons why carbon is the sort of fundamental backbone of the way life operates on the Earth. The flexibility in redox states and bonding configurations that carbon exhibits, I think, makes it exceptionally suited to serving diverse roles, forming a diverse array of molecules that can then undergo some sort of a selection process. Now that's not to exclude a priori other element-based systems. It's just that to chemists and biochemists who study the way molecules are formed or the way they could be formed in the early Earth, it does make a lot of sense that carbon is the basis for that. What Madhu discussed and the observations that Madhu mentioned, including for instance carbon disulfide and other exotic compounds, it just kind of reminds us how naive we are about the full complexity that could arise from combinations of the periodic table. And that's a real challenge. I mean, in order to access that, in order to really be sure, we need to be dealing experimentally with very exotic ranges in temperature and pressure, and that's a formidable but important challenge, I think, in providing experimental evidence to know whether other chemistries are possible.
Yeah, can I just add one point to that, Cathie? So when I said whether we can identify life, the spirit behind that is that we are going to measure, detect, several of these molecules, some of which we know are biomarkers on Earth, and others could be poisonous to some life on Earth. But based on those measurements, it would be too quick to jump to conclusions of whether that indicates life or doesn't indicate life, because there could be some other biology even within carbon-based life. There is a wide diversity of life that can happen, right? And what I meant is that there could be even carbon-based life that doesn't occur on Earth but occurs on some other planet, which could give an entirely different atmospheric chemistry. So when we measure these molecules, like Nick pointed out, dimethyl sulfide or CS2 or any other molecule, even from carbon-based life, we want to be careful how to interpret it and to extrapolate it to what kind of life could be giving that.
Thank you. And on that point, I mean, we're having questions about whether life necessarily involves DNA, for example, and also whether free oxygen is necessary or sufficient as a life indicator. Do you want to just briefly speak to those two things?
Yeah, for the second one, the free oxygen bit, there have been theoretical studies which showed that you can have oxygen in the atmosphere just photochemically especially around rocky planets, around M dwarfs. So just detecting oxygen is not a sure shot indicator. The prevailing wisdom now is that any one molecule won't be conclusive. You need like combinations of molecules, pairs or 3 or 4 molecules that you basically triangulate to establish that no combination of geological or atmospheric processes can do that. So that's the current wisdom. I'll request Nick to answer the DNA question. You may be closer to that.
Anything to add there?
Yeah, that's right. I mean, DNA, well, so DNA, solves life's problem of needing to store information and transfer it, to subsequent generations. That this is an essential feature of how we understand that life operates on the Earth. There has been a lot of thinking and research done on alternative ways of information storage, at least from the standpoint of other nucleic acids on the Earth. That's quite a specific problem that kind of arises from our own biochemistry. That it's a broader question of how, the other ways that information could be stored in the molecular sense under some very exotic conditions. I don't think we have a good answer to that yet.
We're running out of time, which is a great shame because there are so many questions and they keep on popping up. I'm just going to select one question, which is for Madhu, because it's just that what is the weirdest observation regarding exoplanets you've come across so far?
So I've been working, as you know, Cathie, for the last close to almost 2 decades, and we've seen a lot of strange planets, hot Jupiters, magma worlds, and these planets. But I must say that the latest observation, this K218b, was a shocker of a lifetime, because even before the observations, we dreamt up these kinds of planets when we said, maybe these kinds of planets would be out there. Let's point JWST at it and look. So we weren't expecting to make any robust detection. There was just like 14 hours of observation, one transit in each instrument. And then the spectrum that comes out with all these nice features that you can tell by eye, to me, that was like a big, big breakthrough. And to most people in the field, regardless of the interpretation, to be able to see that kind of spectrum for a habitable zone planet was a revolutionary time. And I went through like a long time of just adjusting to that result, because we are not used to seeing such data for small habitable zone planets. And then, of course, the interpretation of it, and when the story comes together, that actually that the composition we are seeing is consistent with what was predicted by ourselves and several other groups before the observation was taken. So as you know, in astrophysics, it's very rare that you make a theoretical prediction and then observation sort of confirms that, even though there could be other explanations, but that's a rare moment in astrophysics and astronomy. So to me, that was a weird experience, and the whole developments after that with new observations as well.
Well, thank you very much for that. And you're quite right that post-dictions rather than predictions tend to be more the norm in astronomy. So it's very satisfying when it works the other way around. Well, this has been really fascinating. I think we could probably all sit here for another half hour, but sadly, this is the end of the webinar. If you're enjoying webinars in this series, please look out for the next one, which is How Natural Are Natural Hazards, which will be on the 13th of March, and details of that can be found on the alumni website. So it only remains to me to thank our speakers and to thank all of you who've put in wonderful questions, including those that we haven't been able to cover. There's so much depth and richness in them. Thank you very much, everybody, and good afternoon.
Thank you, everyone.
Thanks.